There's a characteristic of enthalpy which makes it easier for chemists to calculate the enthalpy change, or the heat given off or absorbed, for reactions that might otherwise be difficult to measure experimentally. And this characteristic is summarized in Hess's law, which states that the change in enthalpy for a reaction is independent of the path of the reaction. In other words, what matters in the total heat exchange is what are the starting reactants and what are the final products, not how you get from the reactants to the products. And by way of illustration, we're going to use this reaction, carbon solid, which is carbon graphite, the stable allotropic form of carbon at 25 degrees and 1 atmosphere pressure, combusting an oxygen to produce carbon monoxide gas. The enthalpy change, or the heat exchanged in this reaction, is difficult to measure directly. But luckily, since enthalpy is a function of state and independent of the path, we're going to be able to measure this heat change indirectly. So to just further illustrate what we mean by this state function, or a function that's independent of the path, we're going to use an example that might be a little more intuitive, and that is the potential energy of an object. So this is a rough drawing of a mountain. It doesn't look much like a mountain, but there you have it. And let's say that you and your twin, or your friend, either way you have the same height and same weight. You're starting from this position and you're going to do a hike up to the top of the mountain. Now, you decide that you're going to take this path up to the cliff, and your friend, or twin, let's say your twin, who's the same height and weight, takes a path that goes over the top of the mountain. Now, the potential energy change that you undergo in traveling from the bottom of the mountain to this cliff is independent of which path you took up the mountain. It only matters where you started and where you ended up. Okay? So the enthalpy change for a reaction is similar. It's only going to be dependent on what are the starting reactants and what are the final products, not how you actually get from the reactants to the products. So we're going to illustrate this idea that enthalpy change is independent of the path, and use it to calculate the enthalpy change for this particular reaction. So we can't measure this one directly, but we do happen to know, for the sake of argument, that the combustion of carbon to produce CO2 has an enthalpy change of minus 393.5 kilojoules per mole. And let's say that we also know that the combustion of carbon monoxide and oxygen to produce CO2 has an enthalpy change of minus 283.0 kilojoules per mole. Well, how is this going to help us determine the enthalpy change for the original reaction that we're interested in? Well, you'll notice that carbon graphite appears on the reactant side of the equation of interest, and this first equation for which we actually know the enthalpy change. Carbon monoxide, however, is a product in the reaction we're interested in, and it's a reactant in this reaction for which we happen to know the enthalpy. However, if we flip this reaction around, so in other words, write it as the decomposition of CO2 to produce carbon monoxide and oxygen, now carbon monoxide is on the product side, as it is in the equation we're interested in. And we still know the enthalpy change for this reaction. It's going to be the same but opposite in sign, so positive 283 kilojoules per mole. So now it might be starting to become clear where we're going with this. We have two reactions. Combustion of carbon and oxygen produce CO2, and then the breakdown of that CO2 to produce the carbon monoxide that we're interested in. So what we're doing is, instead of a one-step process for producing our carbon monoxide, we're undergoing a two-step process. However, the total enthalpy change, because it's independent of the pathway, will be the same regardless of whether we did it in the two steps or the one step. So now, using our two steps, we can calculate the enthalpy change for our original reaction. First, we're going to add the reactants and the products on the two sides of the two reactions. So we're going to sum the two reactions. So we have now carbon plus oxygen plus CO2 to form CO2 plus carbon monoxide and 1/2 O2. Now you'll see that there are reactants and products in common on both sides of this equation, which will then drop out. And that leaves us with carbon solid plus 1/2 O2 to produce carbon monoxide. So what this is showing is that the net result of our two-step process is the same as our one-step process. It's the combustion of carbon and oxygen to produce CO. The enthalpy change for our two-step process will be the sum of minus 393.5 kilojoules per mole plus 283 kilojoules per mole, which is 110.5 kilojoules per mole. And this is the enthalpy change also for the original reaction because, as is stated in Hess's law, the enthalpy for the reaction is independent of the pathway.